Honored Nobel laureates, Your Excellencies, distinguished colleagues, dear students, ladies and gentlemen, a warm welcome to the 2024 Nobel Lectures in Physics. This year's Nobel Prize in Physics is about artificial neural networks and their central role in the revolutionary development of machine learning. Machine learning is the ability of a computer to learn from examples instead of following instructions of programmed recipes. Artificial neural networks are the foundational building block of machine learning. By feeding a neural network with large amounts of data, be it images, speech, or music, it is trained to recognize patterns. Once it has learned to find these patterns, it can generate new data that resemble the ones in the given data set. Giving it millions of pictures of cats, it will learn what a cat looks like and how it differs from a dog, without having to follow gradually narrowing programmed subroutines describing the taxonomy of mammals and the meowing and purring sounds that they make. I do not need to convince you that today this new technology has drastically changed our daily lives. Also in research areas as diverse as particle physics, protein crystallography, material science, astrophysics, artificial neural networks have contributed to discoveries and inventions of great importance. But how did it all start? How are artificial neural networks built, and how do they work? As long ago as the early 1980s, this year's Nobel laureates, John Hopfield and Geoffrey Hinton, made foundational discoveries and inventions that enable machine learning with artificial neural networks. Incurably curious about how our brain works, with the billions of neurons wired together by uncountable connections, they searched for answers to the questions of how we humans learn, how we process and categorize information, and how we recognize new information by association to the stored memories in the data set, to the stored memories and experiences, John Hopfield made groundbreaking contributions by describing the dynamic model of associative memory using fundamental concepts from physics, the physics that describe collective phenomena. He used the same equations and models that govern the physics of magnetic materials to describe the interactions in the brain. Geoffrey Hinton applied concepts from statistical physics to develop efficient neural networks with multiple layers. He developed learning algorithms and methods for the networks to self-improve. It's now my pleasure and great honor to introduce our first speaker, John Hopfield. John Hopfield was born in Chicago, 1933. He received his first degree from Wethmore College in 1954. He earned his PhD in 1958 from Cornell University. He was appointed professor of physics at Princeton University in 1964. And in 1980, he became professor of chemistry and biology at California Institute of Technology. He returned then to Princeton University, where he presently is affiliated as Emeritus Professor in Molecular Biology. Please join me in welcoming John Hopfield to the stage to tell us about the developments that led to this year's Nobel Prize of Physics.
Thank you for the introduction. Thank you, thank you. Thank you for coming. There we go. My first full-time employment was at the Bell Telephone Laboratories, where the transistor had been invented 10 years earlier. I joined its 6-person theoretical physics group in March 1958. A full half-day of employment was spent on administrative detail. I headed for my new office. Unpacking a few books and journals took an hour. A visit to the fifth floor stockroom produced some lined tablets, pencils, and a hand-cranked pencil sharpener. I returned to my office and sharpened several pencils. Now what should I do? That stark question has plagued me many times in my research and teaching career. Every scientist, every scholar faces this vexing issue of what to work on each day. Most respond by working today to extend a little yesterday's line of thought or line of measurement, or plot development. Most of us spend little time thinking seriously about choosing the research area we next pursue. You hear very few lectures on how to choose a research direction. Yet the choice of problem is the primary determinant of what one accomplishes in science. 2 papers that I wrote more than 40 years ago form the basis of the work often referred to as the Hopfield model. I will first describe how the subject developed, some of the choices made, the situations encountered, ultimately defining the germ of a useful viewpoint on which mathematics could be overlaid. For shorthand, I refer to this process as problem choice, but it really is a description of how a useful point of view was winnowed from an analysis of random events from my past. When viewed with historical hindsight, the development of a problem is often presented as a logical sequence of correct choices. In a branching decision tree. Without the benefit of hindsight, research is often pursued in random directions, taken with no overwhelming insight. To me, growing up with a father and mother, both of whom were physicists, physics was not defined by subject matter. The atom, the troposphere, a piece of glass, my bicycle, a magnet, the atom, these are all incidentally the subject matter. Physics was a point of view that the world around us, with effort, ingenuity, and adequate resources, is understandable in a predictive and reasonably quantitative fashion. Being a physicist is a dedication to a quest for this kind of understanding. Of course, neither of my parents ever spoke of what defines physics. It was only much later that I thought about how my upbringing had defined a useful worldview. I grew up taking things apart, seeing how they worked, repairing bicycles, exploring chemistry, building flyable model airplanes, crystal sets, and simple radios, playing with batteries and learning to think with my hands and manipulate real objects. Each thing I understood, why my bicycle brakes got hot when they were used, how a consistent story could be incorporated as a small part of a much grander understanding in a complicated system. Heedless of the financial consequences of being a physicist, I only briefly considered an alternative career. My high school chemistry teacher had been superb, while my physics teacher lacked an understanding even of the rudiments of electricity and magnetism. Thus influenced, when listing potential majors on college applications, I wrote physics or chemistry. At Swarthmore College, I was assigned Professor William Elmore as my advisor. We met in his office to discuss my future. He located the student card describing my high school record and thus the field of study I was interested in, took out a pen and crossed out 2 words, remarking, "I don't believe we need to consider chemistry." And that is the way my education went. An arbitrary act by Bill Elmore had much to do with my being here today. I began looking at graduate schools in physics with an eye to what I might specialize in. My upbringing had particularly focused my interest on the physics of the daily world and its technologies. I went to graduate school at Cornell because in 1954, Cornell had a segment of the physics department interested in a field called solid-state physics. In the middle of my second year at Cornell, I approached theoretical physicist Albert W. Overhauser to ask if he would supervise my thesis and help me find a thesis problem. Through courses and doing problem sets, I was rapidly acquiring the tools of theoretical physics, but I had no idea of how to find an appropriate research problem. Happily, Overhauser had a list of interesting puzzles. They were often in the form of a paradox, elementary theoretical analysis of a particular phenomenon in solid-state physics gives result B. Root A over here is what experiments get, and they're totally different. In most paradoxes in this list, Overhauser himself had no idea of what was producing the conflict between a common-sense theoretical view and the experimental facts. I picked a problem having to do with the radiative lifetime of an exciton in a crystal. Overhauser was enormously supportive as a listener and a critic when I went to see him, but finding direction and resolving technical theoretical issues were entirely my problem. The great gift he gave me was the ownership of an interesting question and total responsibility for research and progress. I've done my best to repay my mentor Overhauser through similarly nurturing another generation of independent students, a couple of which are actually here today. PhD in hand, I took a position in the theory group at Bell Laboratories. Conyers Heading Carnes Herring was head of this group and saw me struggling to identify my next problem to work on. He suggested visiting with experimentalists to get my own sense of where interesting puzzles lay. This was the framework within which I met chemist David Thomas, and we formed a working theory-experiment alliance. It was to provide me with unanticipated problems and paradoxes for 10 years and provide AT&T with a major knowledge base in compound semiconductors. It garnered David and me a joint Oliver E. Buckley Solid-State Physics Prize from the American Physical Society in 1969. At the time, no one would have guessed that the combination of light and compound semiconductors would have a major technological role in the future. By 1968, I had run out of problems in condensed matter physics to which my particular talents seemed useful. I went to the Cavendish Laboratory of Cambridge University in the UK on a Guggenheim Fellowship for half a year, hoping to find new interesting avenues, but found little for me. Returning from Cambridge to Princeton University and my consultancy in the semiconductor group at Bell Labs, I ran into Robert J. Schulman, a chemist who was doing the first high-resolution nuclear magnetic experiments on hemoglobin. Bob told me about the cooperative oxygen binding at the 4 iron atoms in the center of the widely separated heme groups of the protein. An incredible panoply of physics techniques was being used to study the molecule: NMR, EPR, optical spectroscopy, neutron scattering, Mossbauer spectroscopy. All the clever experimental techniques of solid-state physics seemed relevant to understanding hemoglobin. Hemoglobin provided me a simple entree from condensed matter physics to biological matter physics. In both fields, the goal was to understand how structure and low-lying excitations were related to measurable and relevant properties. It seemed that my background in condensed matter physics might find good use in biology. When Linus Pauling, a double Nobelist in chemistry and in peace, was asked about choosing problems to work on, he remarked, "I ask myself whether the problem I am considering is one to which I am likely to make a contribution." I would clearly need to emulate Pauling. I had become interested in the unexpectedly small number of mistakes made in choosing the correct amino acid when the next amino acid is inserted in a protein during protein synthesis within a cell. How might I make my physics background more likely to see a solution to this problem? Free energy is the key. High-energy molecules like glucose or ATP are expensive for a cell to make, and a biochemical process using unexpectedly large numbers of high-energy molecules in a simple process must be paying dearly for that cost for a purpose. Suppose that the purpose was to proofread, to remove biosynthesis errors. Perhaps experimental biochemists had not noticed because they did not know how to look. I was successful in that problem. I found a plausible scheme for proofreading and protein synthesis based on known biochemical detail and described critical experiments to test the theory. I gave a talk at Harvard Medical School in 1976, ending with a brief account of proofreading and my prediction about non-stoichiometry in protein synthesis. The first question after my talk was Robert C. Thompson. He asked, "Would you like to hear the results of such an experimental measurement?" And went on to describe his experiments, not yet published, in measuring the stoichiometry ratios when a system was being pushed to proofread and when it was not. He described experimental facts which just overwhelmingly pushed the idea proofreading works that way. It was one of the biggest and most delightful surprises of my brief career in chemistry. Now, let's see if I can get this right. Yes. This 1974 paper was important in my approach to biological problems, for it led me to think about the function of the structure of a reaction network, rather than just what is the function of the biological molecule. 6 years later, I was generalizing this view and thinking about networks of neurons rather than the properties of single nerve cells. Writing this paper, doing this research, also led me to think more about problem identification and biophysical research. The unexpected success of this paper was due to its formulation of a new biological problem and had nothing to do with my knowledge of biochemistry or biophysics. Chance had favored the unprepared, but the inquiring mind. I spent the winter of 1977 at the Bohr Institute in Copenhagen as part of its sporadic but historical outreach toward biology. My task was to run a broad Modern Biology for Physicists seminar series. In 1932, Niels Bohr had opened the International Congress on Light Therapy with a lecture entitled Light and Life. Bohr asked whether a deep explanation of life itself and the philosophical ambiguities of how to interpret quantum mechanics were intrinsically intertwined. However, in 1977, my distinguished experts in biology emphasized what they understood. They certainly did not describe biological science as being in need of help from physicists. I returned to Princeton without a new problem for myself. I was now looking for a big problem whose resolution and understanding will be of significance far beyond its normal disciplinary boundaries and will reorganize the fields from which they came. Bold, prone to failure. My Princeton University office telephone rang shortly before my morning class, expecting a call about important things, tennis. I answered only to find Francis O. Schmidt on the line. He said he ran the neuroscience research program at MIT, would be transiting Princeton next Wednesday, and would greatly appreciate a half hour, no more, of my time. I had never heard either of Schmidt or the NRP, needed to head off. That's what I'm supposed to avoid. Yes. For needed to head off for lecture, thought, what's 30 minutes, and agreed to meet. The following week, Francis O. Schmidt descended on me. He described his neuroscience research program, which chiefly held small meetings in Boston, attended by 20 regular members and 20 visitors. I told him I knew nothing of neuroscience. He said, "That doesn't matter. Just speak on what interests you." So I talked about my theory of kinetic proofreading and the general issue of accuracy in biosynthesis. The audience, neurologists, immunologists, electrophysiologists, neuroanatomists, understood little of what I said. It didn't matter. Frank wanted to add a physicist member to the group, hoping to bring someone with diverse science experience to interact with his subject and perhaps help it become more integrated and a more predictive science. I was captivated by the talks at the meeting. How mind emerges from brain is to me the deepest question posed by our humanity. It was being pursued in narrow slices as little problems by the NRP Club of Scientists with diverse talents and great enthusiasm. But it appeared to me that this group of scientists would never possibly be able to address the big problem, because the solution can be expressed only as an appropriate mathematical language and structure. None then involved with the NRP moved easily in this sphere, so I joined the group hoping to define, construct, or discover something I could usefully do in this field. My basic education in neurobiology came from attending the semi-annual NRP meetings, sitting next to world experts in their field who would patiently explain to me what the speaker was really trying to talk about. I tasked myself with finding an integrated physics view that's what I've done wrong. Yeah. Of trying somehow to rise above the disjoint details of lectures, neuroanatomy, electrophysiology, learning in the rat and Alzheimer's disease, and find some kind of integrated structure to theory. In 1979, Caltech appointed me to a professorship jointly between chemistry and biology, and I left Princeton. The quantum computing facility at Caltech was a splendid environment for trying out models. It supported multi-user real-time computing, video displays, direct keyboard input, all things you say are trivial, but in 1979 they were a marvelous thing to discover. My insight was that basic machine or brain operation computed by following a machine trajectory in state space from the beginning where you put the program and data started, and then every tick of the clock, the state of the system moved. Ultimately, the state stopped changing. When the state stopped changing, the computation must be done. You'd read out some of the registers, and the computation had actually been done by following a dynamical trajectory from start to end. That trajectory needs stability against perturbations to reach a correct answer in spite of noise and system imperfections. This picture of batch mode digital computation is just a schematic to try to, just try to get the impression of here's what Hopfield views as computation. I turned finally to a more specifically chosen question than just a general one, and trying to focus on something which an animal needs, or animals are known to have. And this turned into something which became fundamentally related to behaviors that a psychologist might call associative memory, or an engineer might call content addressable memory, or another psychologist would describe this as declarative memory, something you can describe. And these names share a common feature. They share a common basic paradigm that can be described as computing by a dynamical system which follows a trajectory which is stable, and thus small perturbations away from that trajectory are squeezed back onto it, and that's the way you go from the start to finish in a noisy system. That's what content addressable memory does in a very different regime. But all of these, a whole bunch of things associated, I can't get by without using that term. I'm exercising, of course, associative memory as I speak. But all these things require what a mathematician would describe as convergent flows. Once I grasped that point, I had heard enough about the mathematics of spin systems as they are related to magnetism and complex phenomena in magnetic materials. I'd been at Bell Labs enough to be around when people were seriously talking about these subjects, and so I knew something about the connection between spin systems and trajectories. And I only had to say, let's make the biological system look like a spin system, and then they should have the same kind of mathematics. Associative memory is reciprocal. Seeing someone reminds you of remember their name, and hearing their name reminds you of what they look like. That fact can be expressed in a network structure by making connections that are reciprocal. The mathematics of such networks is closely related to the mathematics of spin systems as seen in solids, and to things having to do with their phase transitions in magnetism. Suddenly there was a connection between neurobiology on the one hand and the solid state physics I sort of knew on the other. One way to achieve a convergent flow is for a state to be associated with an energy and have the allowed transitions state to state to state allowed such transitions to take place only if the energy was decreasing. Like a ball rolling downhill on a rough terrain. If you want to understand the trajectory of the ball, you could follow the terrain and the ball in detail, or you can understand there's an energy. The whole thing is just going downhill, and you go from near the top of the hill to near the bottom of the hill. And the energy function is what you really need to understand convergent flows in a wide range of systems. With that connection made, 3 months later I was writing a paper. Everything really came together when I see these two parts of science are really being described by the same set of mathematics. Then now the problem became of writing a paper. I had 3 target reader audiences for such research: physicists, computer scientists, and neurobiologists. Disparate set of people, but being a member of the National Academy of Science, I could publish a paper in PNAS, Proceedings at the National Academy, without review. But for PNAS, there was an absolute 5-paper limit on article length, including references, and there were these 3 different audiences to address and much to say. I had to write science in the style that Hemingway wrote nonfiction. In hindsight, the omission of the almost obvious increased the impact of the paper. The unstated became an invitation for others to add to the subject, and thus encouraged an expanding community of contributors to work on such network models. This 1982 paper is the first publication in which I used the word neuron. It was to provide an entryway to working in neuroscience for many physicists and computer scientists. Further work connected these networks to many significant applications far beyond associative memory, including the emerging field of artificial neural networks. It also brought many statistical physicists into the field and created a foundation for subsequent development of the Boltzmann machine. Continuous associative memory networks also served as inspiration for continuous recurrent networks frequently used in many contemporary AI systems and in complicated computational neuroscience. One issue with what is now called the Hopfield model network of associative memory is that it has a small information storage capacity. Biological networks can store many more memories than the number of sensory neurons and can dynamically adapt these memories if the environment changes. I was jolted into thinking about this problem in 2015 when I was a visiting professor at the Institute for Advanced Study in Princeton and was starting to interact with Dmitry Krotov, a former high-energy theorist who was searching for an interesting problem to work on. After several months of discussion, we formulated a simple mathematical model in which the memory capacity becomes decoupled from the dimensionality of the space. This new model allows for a denser packing of memories, and we called it the dense associative memory as a result. Looking forward, we hope that the idea of useful computation by physical systems will not only become helpful in hindsight for interpreting computational algorithms in existing AI architectures, it may also inspire a new generation of collective physics-inspired AI networks. What I have done in science rests on the experimental and theoretical studies of experts. I have great respect for experts willing to interact with those outside their disciplines, welcoming physics into new territory. Physics at its best is a point of view for understanding the totality of man and his universe. Thank you.